Network speed is often perceived as a software problem, a matter of writing better code or compressing data. However, the movement of information is ultimately governed by the rigid constraints of hardware and physics. Moving data requires a computer to physically push electrons or photons onto a link. We call the time required to squeeze a specific packet onto the wire the transmission delay. It is calculated by dividing the length of the packet by the link's bandwidth. Once the data is on the wire, the signal must travel the geographic distance to the receiver. This is the propagation delay, a value strictly governed by the speed of light within the medium. We quantify network performance through protocol efficiency. This is an algebraic ratio comparing useful transmission time against the total round-trip time required to send a packet and receive a confirmation. Engineers use automatic repeat request, or ARQ, protocols as mathematical frameworks to optimize this efficiency ratio. Because the speed of light is constant, propagation delay remains fixed over a set distance. To improve throughput, protocols must manipulate time and local memory to keep the physical link active for as long as possible. Stop and wait is the most elementary ARQ protocol. Its operation is defined by two rigid sets of rules for the sender and receiver. Under Sender Rule 1, the system transmits exactly one data packet at a time. Sender Rule 2 then forces the system to halt all operations until an explicit acknowledgement, or ACK, returns from the receiver. A visual timeline reveals the cost. The sender transmits a packet, which traverses the link. Only after the receiver processes it can the acknowledgement return. This creates a massive idle gap where the physical wire transmits zero data, wasting bandwidth. Visually, the total round-trip time is the sum of the initial transmission delay and the two-way propagation delay. Expressing this as an efficiency equation proves the mathematical flaw. As propagation delay increases, the denominator grows and efficiency drops. On a high-latency connection, like a satellite link, the propagation delay is so large that stop-and-wait efficiency near zero, effectively starving the network of throughput. The sliding window concept eliminates these idle gaps. It allows the sender to transmit a burst of W packets before pausing to wait for an acknowledgement. The go-back-n protocol applies this by expanding the sender window size to a variable value n. While sender capacity grows, the receiver window is fixed at 1, accepting only strict sequential packets. But with a sender window of size n, multiple packets fire in rapid succession, filling empty time blocks and saturating the transmission line. To maintain order, the receiver uses cumulative acknowledgements. It only confirms the highest consecutive sequence number successfully received, rather than acknowledging every individual frame. The efficiency formula for go-back-n reflects this improvement. By multiplying the transmission time by the window size n, we significantly increase the numerator. By utilizing local memory to buffer n unacknowledged packets, the sender keeps the physical pipe full and bypasses the round-trip delay bottleneck. In real-world environments, physical channels are susceptible to noise, which leads to corrupted or dropped packets. Consider a sliding window where packet 2 is corrupted during transit. While the sender continues its sequence, packets 3 and 4 still arrive successfully at the receiver. Because the receiver window size is only 1, it cannot accept out-of-order data. Its logic is locked onto packet 2. Consequently, the receiver discards the perfectly valid data in packets 3 and 4. When the sender's timer for packet 2 expires without an acknowledgement, the protocol initiates error recovery. The sender must go back n and retransmit every frame starting from packet 2, forcing the system to resend data already successfully received. While go back n solves the latency issue, it introduces significant bandwidth waste during noisy conditions, necessitating a more granular approach to error handling. Selective Repeat ARQ eliminates the waste found in go back n. Its primary rule scales the receiver window to match the sender window size exactly. An expanded receiver window accepts out-of-order packets. If packet 2 is lost, the receiver buffers packets 3 and 4, issuing independent ACKs for them, plus a NAC for the missing frame. The sender retransmits only packet 2. Upon arrival, the receiver resorts the window. Selective Repeat preserves bandwidth by isolating errors, though it requires more complex searching and sorting logic at both ends of the connection. Modern protocol design relies on a menu of mathematical trade-offs dictated by hardware capability. The evolution of efficiency across these three methods shows the transition from the bottleneck of single-packet transmission to the high-throughput multiplier of the sliding window. These performance gains require a linear increase in hardware memory. The buffer requirement scales from a simple baseline of 2 packets up to 2n for the selective repeat protocol. Higher speeds also demand more complex sequence numbering. To prevent window overlap, the pool of available sequence numbers must be at least as large as the combined size of both windows. Achieving maximum throughput requires an algebraic balancing act, trading local memory and processing power to keep the global physical pipe continuously saturated.